Alrighty, now this video is going to be introducing optics. Of course, a new topic. We're going to have new equations, new ways of thinking about things, and we're going to cover it at a fairly generalized level. Obviously, when you continue to pursue physics and engineering and things like this, we're going to learn more about optics, get deeper, more details, more subtopics into this subject. But for now, we're going to learn the basics, the fundamentals, and some of the important kind of calculations you can do with optics. So first, of course, optics is basically the study of light. Let's see. In order to study light, of course, we need to know what is light. And light, formally, is what's called electromagnetic radiation. And so what is this? Of course, you could look at the word and figure out what it means. First of all, radiation. Radiate means to send out, basically. And electromagnetic is a combination of electricity and magnetism. And it turns out, this wasn't always known, obviously. This was learned fairly recently in the study of physics, that electricity and magnetism are not two separate phenomena. They're actually the same phenomenon, or at least there is a major phenomenon called electromagnetism, and electricity is an aspect of it, and magnetism is an aspect of it, but you basically don't have one without the other. And when you learn about electromagnetism, especially in more advanced physics classes, you learn how this is so. Things like induction, where if you have electricity, you have a current flowing through a wire. That means you have moving electric charges, and these moving electric charges, by their nature, induce a magnetic field. And so, in fact, if you look deeply into what is magnetism, what causes magnetism, fundamentally, a magnet or magnetic properties arise from the motion of electric charges. So you can't have magnetism without electricity. Electricity causes magnetism. And by its nature, if you have a magnet, or you move a magnet, or you change magnetic properties, you inevitably induce electric phenomenon to happen. So, this gets to electromagnetic radiation. What is it? We don't have to get too specific about it, but just so you have a general knowledge of what light is, it's a wave which propagates through space. What is waving? So, for instance, if you think about sound waves are basically the molecules of the air being forced to kind of squish together and come apart by pressure. You push on the air, and the frequency of the vibration of the air being pushed gives rise to sound. So it's the air molecules, and it's the propagation of the pressure through the air molecules that give rise to sound waves. Water waves, of course. You have water. There's some pressure or something in the water, and it's the water molecules that are waving up and down as it propagates through the sea. So what is waving for light? it turns out that what waves, because light can travel through a vacuum where there are no particles, so sound, you have to have air. If there's no air or some material, like sound can go through a wall or it can go through water. It doesn't need air, but it needs a material to go through. If you're out in space, a pure vacuum, where there's no molecules, then there's no such thing as sound, because there's nothing to pressurize. But that's not true for light. Light can propagate through a vacuum. So what is the thing which waves? And it turns out that it's the electric field and the magnetic field. So the way one looks at it, and I'm not going to be able to draw this very well, but you can always Google this and get a nice three-dimensional picture, is you have the electric field waving up and down as the light wave is propagating to the right, let's say. And then the magnetic field, which is going to be perpendicular to the electric field by its nature, will also wave. And so think of this as coming in and out of the page. Again, I can't really draw this too accurately, but I hope you get kind of an idea so that, you could think of this as the center line. The electric field is waving up and down, and the magnetic field is waving out towards you and into the page, and out towards you and into the page, 90 degrees. And that oscillation of the electric field and magnetic field as it propagates through space is what we see as light, is electromagnetic radiation. And obviously, as I said, there's a lot of specifics we're not going to worry about because I want to get more into what kind of calculations we could do for this class. But we know there's a spectrum of light. So we have things like radio waves, radio, the signal you get in your radio, that's light. What your radio is picking up by its antenna is light whose frequency is very low. Very low frequency, low energy, very long wavelength. That's called radio waves. And you have other things like microwaves. So when you stick something in a microwave to heat it up, basically what's happening is the box is sending light into the material. The light is oscillating. The electric and magnetic fields are oscillating at a certain frequency. And it just so happens that this specific range of frequencies is such that it will vibrate water molecules. And that vibration of the water molecules causes things like friction, and it basically heats up the water in the food by vibration, and thus heats up the actual material of the food. So microwaves, that's another form of light, just a different frequency. And of course, there's a whole bunch of things. I'm not going to get into all of them, but we have the visible, so things we see, colors. So anything you actually look at, that's light, obviously. You're seeing the light reflecting off of an object or coming from a source. And the different colors are just different frequencies of that light, the oscillation. But then there's more. Of course, you've got things like X-rays, you've got ultraviolet, you've got a gamma, which are the highest, and so forth. All different. They're all light. It's just how fast does the light vibrate, oscillate, let's say. And we give them names for particular ranges. If it oscillates between this many times and this many times a second, we call it radio. But there's no difference between radio light and microwave light or visible light. It's all light. It just waves at a different frequency. So that's light. That's all it is. What's important? Light always moves at the speed of light, by definition. The speed of light has a very special variable, c. And it's basically, just rounded numbers, is 3 times 10 to the 8th meters per second. That's how fast light travels. Now, this is how fast light travels through a vacuum, through, let's say, the air. Of course, it's slightly slower in the air. And in water, it moves at a different speed. In glass, it moves at a different speed, and all sorts of things. But if we're talking about light propagating through space, it always moves with this specific velocity. Always. And no matter when you measure it, whether you're moving when you measure it or the source of the light moves, you always get this particular value. And it's that fact which gives rise to special theory of relativity by Einstein. The fact that if, let's say, you're in a car and a car's traveling 30 meters per second, and you have a ball in your hand and you throw the ball, and you're only so strong and the velocity you throw the ball at is 10 meters per second. Well, someone out here looking at the ball, they're going to see the ball leave from the car, measure the velocity of the ball, and they'll say, oh, the velocity of the ball is 40 meters per second. Because the car's moving 30, so if you don't throw the ball, if you're just holding it, it's already going 30. But then you throw it and give it an extra 10 meters per second, so a person measuring the ball will see it moving at 40. And that makes perfect sense. And the same would hold true if the car is not moving, but you, as an observer, are moving towards the car at 30 meters per second. Well, if you're moving towards the car, the person throws a ball at 10, but you're already moving 30 towards it, again, you're going to see the ball move towards you with a speed of 40. However, light doesn't work this way. If instead of a ball, the person in the car is holding a flashlight, and he sends light, he turns on the flashlight and the light propagates, and this person's trying to measure how fast the light comes towards him. Let's say the car is moving with a velocity of, half the speed of light. So very, very fast. So the person's looking at the car, it's coming at him already at half the speed of light, and then the person turns on the flashlight. Well, one would imagine when you measure the speed of the light, it would be however fast light travels, which is c, plus however fast the car was already moving, just like in this case. However, that's not what happens. When this person measures the light, they only see it coming at them at c, regardless of how fast the car is moving. And it's only light that works this way. And this is what caused Einstein, when he thought about this, because there were observations. The observations said speed of light. And there's always the speed of light. And of course, Einstein theoretically assumed it to be true as well. He was pretty smart in this way. And so what Einstein had to do was figure out if it's true, which it is by observation, that no matter what's happening to the source of the light or the observer, however fast they move, every observer will always see the speed of light as this particular number. Never bigger, never smaller. If that's true, then it must be true that time slows down when an object moves, and that spatial distances change. They get smaller. So for instance, it's a way of saying, well, if I'm trying to measure the speed of light, how do I do it? Well, I need a meter stick so I know how far something goes, and I need a stopwatch to know how long it took. If I know how far something goes, how long it took, I get the speed. Well, in order for the speed to always be the same number, then those other two things must be changing in such a way as to always produce the same number. And that's what the special theory of relativity does. There's a very formal mathematical construction for calculating. Sorry about that. For calculating how the lengths of space will change or how time changes based on how fast you move. So, that's basically an introduction to special relativity. As I said, with more advanced courses, we learn how to do these calculations, and there's a little bit of math involved and things like that. Next, what I want to talk about is what's called refraction. And refraction is an effect that is observed with light, where when light travels, for instance, let's say here's some water. So down here is water, up here is air. And light's coming in, it hits the surface of the water. And what we find, if we measure the angle, call it theta I, which means angle of incidence. Note here that the angle is always measured with respect to what's called the normal, and normal means perpendicular in physics. So the angle is always measured with respect to the perpendicular line, which in this case is vertical, the dashed line. If we measure that angle, it's some number, let's say it's coming in at 30 degrees, whatever it is. Well then, when it hits the water, we find, strangely, that the angle changes. There's some new angle called theta R. That's called the angle of refraction. And so what we see is the light seems to bend when it goes from one medium to another. When light travels from the air, hits the surface of a pond or something, the light continues into the pond, but instead of it continuing to travel in the same straight line it was, it's now traveling in a slightly different direction. And the question is, why does this happen? And can we calculate, can we predict how it will happen? What will be these angles? If we know the angle coming in, can we predict what the angle coming out will be? Well, in order to do this, first let's try to figure out why this is happening, or at least get an idea that it should happen. And the kind of example I like to think about is pretend you're in a car. Okay, so here's my little drawing of a car, and let's say this is kind of like a top-down view, and the car is moving this way. So you're driving around in your car, and it had been raining, and over here on the right side of the road is a puddle of water. Well, as the car drives through, all of a sudden, the right side of the car hits the puddle, but the left side doesn't. Intuitively, what happens? Do you just continue on and you don't notice it? Or do you have to hold on to the steering wheel because the steering wheel gets jerked in one direction or another? Well, from experience, I know that what happens is the steering wheel gets jerked in such a way as to try to make the car turn to the right. And so you have to hold on to the steering wheel tight to make sure you continue going straight. And why does it happen? Well, just think about the car. The left side tires are moving along, and all they feel is the road. But the right side tires, when they hit the pond, or not the pond, but the puddle, it's hard for the tires to move through the water. So inevitably, the right side tires, when they hit this water, will slow down a little bit relative to the left side. And of course, if the left side of your car is moving faster than the right side, then the left side wants to move this way and the right side won't move quite as much. So the car tries to turn to the right. Well, it turns out that kind of intuitive thought can be used here for light. Because what we know is that light travels fastest in air. But anytime light tries to go into another medium, it slows down. It can't travel as fast. It's harder to move through this material. And so you can kind of see the same thing happening. If you imagine the light as a kind of thick beam, then, here it is here, then this side of the light hits the water first, let's say, and slows down relative to this right side, which hasn't hit it. So it kind of tries to turn the light a little bit towards the water, in the same way as the car when the right side of the car hits a puddle. Now, this is a simplified view, and there's actually a lot more complication happening, but just intuitively speaking, this is kind of a way of thinking about why it should be that the light will bend when it goes from one medium to another. Now, how do we start doing some calculations? What are some equations we could use here? In order to do that, we first need to introduce something called N, the index of refraction. And what the index of refraction, N, is a measure of the velocity of light in whatever material you're talking about. So, technically speaking, N is equal to the speed of light in a vacuum, c, 3 times 10 to the 8th, divided by how fast light moves in this material. So this is in the material. And this is in vacuum. And so N, the smallest N can be is 1, right? Because the fastest the velocity of light can be is c. So if you have c divided by c, you get 1. That would be the index of refraction of a vacuum. However, if v is smaller than c, that is to say, light in water moves slower than light in a vacuum, then v is a number smaller than c, and so you get a number bigger than 1. And in fact, typical index of refraction you may see, we're going to have air is 1, water 1.33, and glass is 1.5. So these are the indices of refractions we're going to need for our calculations. Obviously, there's different types of water. There's salt water, there's sugar water, and that'll have slightly different numbers. There's different forms of glass. And so this is just an average. On average, glass has an index of refraction of 1.5. We're using some slightly simplified numbers. But we could see index of refraction of glass 1.5 is bigger than air and bigger than water. So that means the speed of light in glass must be smaller than the speed of light in water and smaller than the speed of light in air. It slows down more in the glass, so the index of refraction gets bigger. All right, once we know these, then we introduce Snell's Law. Snell's Law will be the equation we use for refraction. And it's an easy equation to remember. It says N1, that's the index of refraction in whatever medium I'm starting in, times the sine of the incident angle, theta 1, is the same as N2, whatever material I'm going into times sine of theta 2, the index of refraction. And that's it. So, example. Let's take the example I had. Water. Light comes in. It's incident at an angle of 30 degrees. I want to know what's the angle of refraction. That is, what's the angle of the light in the water? Well, first, N for air is 1, and for the water, 1.33. All right, so Snell's Law, that's the equation we use for refraction. N1 sine theta 1 is N2 sine theta 2. We're starting in air, so 1 stuff is air. 1 times the sine of 30. 2 is the thing we're going into, which is water. So N2 is 1.33 times the sine of theta r, which is the thing we want. So I want to calculate this for theta r. How do I do it? Well, first get sine theta r by itself. So sine theta r equals 1 over 1.33 sine of 30. But then notice, I don't want the sine of theta r, I just want theta r. How do I get theta r by itself? I do what's called the inverse sine. I take the inverse sine, of both sides. And the inverse sine cancels the sine, and that'll leave me with theta r is the inverse sine of 1 over 1.33 sine 30. So sine 30 divided by 1.33, inverse sine of that number, and I get 22.1 degrees. Does it make sense? Well, I'm going from air to water. Since the water should be moving slower than the air, my light should have a smaller angle. I should be bent towards the perpendicular. I went from 30 degrees, I'm now at 22. I got to a smaller angle. Makes sense. So I can be confident. And that's how we do angle of refraction. Given air or given light traveling through one medium and going into another, whatever they are, I'm going to use Snell's Law. I have to know 3 of the 4 unknowns. So let's say I'm going from glass to water. Well, I need to know the index of refraction of glass, index of refraction for water, and then either I know what's my angle of incidence, or I know what's the angle of refraction. And then I just try to find the other one. So this is a basic, here's your equation, plug the numbers into the equation style of question. Really not much having to think about anything here. You just have to remember, what's the place I'm coming from? That's 1. What am I going to? That's 2. And then you plug your numbers in. That's Snell's Law, that's refraction. There's one other aspect of refraction we need to know that I want to introduce, and that's called the critical angle. It's an interesting concept. And it's a phenomenon that comes up, and here's how you can see that it comes up. Let's say we have our water. This time, let's say there's someone under the water holding a laser pointer. It turns out that if this person sends the light from their laser towards the surface of the water from underneath, trying to get it into the air, if they happen to do it at an angle called theta c, the critical angle, then instead of the light coming out into the air, what actually happens is the light skims the surface and doesn't actually go into the air. And in fact, if you increase this angle a little bit, so instead of being at theta c, they're at a little bit more than theta c, then it actually bounces back into the water, as if the surface of the water is a mirror. And so what that implies is that someone out here, trying to look, they don't see light coming from the water, because the light never leaves the water itself. It just reflects back into the water. This can't happen the other way. If you're in the air and you shine light towards the water, it will always go into the water. But if you're in the water and you try to shine the light into the air, there are some angles where it won't leave. Now, if you shine it at less than a critical angle, it'll leave. But the critical angle is that very special value where it doesn't leave and it doesn't reflect, it just skims the surface perfectly. Now, is this true or am I lying? Well, it must be true because I'm sure everybody's heard of fiber optics. This is exactly how fiber optics works. Fiber optics makes use of glass fibers. This is kind of a zoomed in view. And light is shown into the glass fiber. Now, glass, of course, is transparent. You can see through it. However, the light is fed into the fiber at just the right angle so that when it hits the surface of this glass, it can't escape. It reflects back. And then when it hits this surface, it reflects back again. And so continues to keep reflecting within this glass fiber until it reaches the end, at which point it could leave the glass. But as it's traveling through this fiber, it's constantly being reflected within, never leaving, even though the glass is transparent. So this is a real thing. If you've ever seen fiber optic Christmas trees or before HDMI, a lot of the stereo receivers and stuff used fiber optical cables. This is what was going on. You're sending light through glass fibers, and instead of the light being able to leave these fibers, they're stuck within it, totally reflecting internally until it reaches the end, at which point it can be input into some other thing. So this is a real thing, and it's an actual phenomenon that's made use of in everyday life. And the question is, how do we calculate that angle which allows this to happen? What is the critical angle? The good news is we don't need a new equation. Let's use Snell's Law. N1 sine theta 1 is N2 sine theta 2. And what I want to find out is, what must theta 1 be to be theta c? That is, what's the critical angle? Well, this is how you calculate it. I'm coming from the 1, so let's say from water, and I'm going into the air, and I want to know what's theta 1 such that it just skims the surface. So divide N1 to the other side, I get sine theta 1, theta c now, is equal to N2 over N1 times sine theta 2. But what's theta 2? Notice, if I'm at the critical angle, then the light skims the surface. So this reflection isn't there. It's just skimming the surface. Well, if that's true, then what angle does my light that's skimming the surface make with the perpendicular line? It's 90 degrees. So theta 2 must be 90 degrees for this to be true. But what's sine of 90 degrees? Sine of 90 degrees is 1. So we get sine theta c is just n2 divided by n1. And thus, solving for theta c, we get the critical angle is the inverse sine of n2 over n1. So, given in a problem, I may say, what's the critical angle of water? How would you solve it? Well, first, you could just memorize this if you want. I don't, because I'll always forget, is it n2 over n1 or n1 over n2? The other thing you could do is just start with Snell's Law, because you already have to know Snell's Law to do the other stuff. So start with Snell's Law and just know that if you want the critical angle, theta 2 is 90 degrees. And then you plug your numbers in. So let's do it for water. N1 sine theta c is N2 sine theta 2. All right, N1, I'm coming from water, so 1.33 sine theta c is N2, 1. I'm going to air times sine of 90. So sine theta c is 1 over 1.33. Thus, theta c is inverse sine of 1 over 1.33, which is about 48.8 degrees. So this says, if you're in a swimming pool and it's a very smooth surface, no waves, and you have a laser pointer, if you shine the laser pointer at the surface of the water from underneath at 48.8 degrees or above, the light will not leave the water. It'll reflect back into the water, so your friend who's outside the pool trying to look at the light will never see it. The light never leaves the pool. It just reflects back. If you shine it at 30 degrees, the light will escape because it's less than a critical angle. The only other thing you have to know is that you can only have a critical angle if you go from a more dense to a less dense medium. So as I said, if I'm going from air and I'm trying to go to water, I can never have a critical angle. The light will always go into the water, never reflect back. But if I'm in the water, which is more dense than air, and I go into the air, I can have critical angle. Or glass. If I'm coming from water and I try to go to glass, glass is more dense than water. I can't have critical angle. But if I'm starting in the glass and I'm trying to get into the water, I can have critical angle. So that's just good to know, because it could save you time on a calculation if I ask you, light is traveling from air into glass. What's the critical angle? Well, you could say immediately, there is no critical angle. However, if I say light is traveling from glass into air, what's the critical angle? Well, start with Snell's Law. Note theta 2 is 90 degrees. And solve for theta 1. So that's critical angle. This will basically conclude what we need to know for refraction. We have Snell's Law, which tells us about going from one medium to another, light will bend. If I'm coming from a less dense medium to a more dense medium, my angle will get smaller. If I go the opposite direction, if I'm coming from water to air, my angle gets bigger. But you don't have to worry about those rules. All you got to do is use Snell's Law, and that calculation will give you the answer. It's very hard to do it wrong. Make sure you're in degree mode on your calculator, and make sure you know which variables are the ones and which ones are the twos. Don't mix them up. Don't have n1 with theta 2 or something like that. Alright, so that's all I have for this video. Be on the lookout for practice problems and the like. And I hope this was helpful.